In example 1 today, so we will look at the normal stress, normal strain correlations. Okay, we have known that normally we use a modulus of elasticity or E, right, to describe this correlation. Right? So in this example, you are requested to determine the downward deflection of point B if the steel rod BC has a diameter of 1.5 inch diameter. Okay, so here the P is given, LAB, LBC, and A has been given. Okay, so this is the structure shown here. Again, in this example, we have to assume that the AB is rigid. Okay, I hope you still remember what rigid means through the examples in chapter 1. Okay, we have a rigid AB, meaning that it will not be stretched, not be compressed, and not be bended. Okay, it will always keep its original shape. But the rod BC here is not rigid. It's stretchable. Okay, so we're actually adding a load P to stretch BC, and so we're calculating the downward deflection of point B or the deformation of BC. Right. So what we are calculating is actually displacement of point B or deformation of BC. Right. Since point C will not will always be there. Point C is a fixed point, is a pin support. Then from C to B, we have this rod. If you are calculating the displacement of point B, it will be equal to the deformation of BC or elongation of BC. Right. So this is what we're calculating, delta BC. Right. So let's do a simple analysis. How can we calculate delta BC? Okay. So how can we calculate delta BC? So we have been given only limited conditions. Okay, you're not knowing strain, but we can calculate it from strain. Okay, we didn't tell you what is the initial length. We told you initial length, but we didn't tell you the final length. So based on the definitions in chapter 1, you have no way to calculate it, right? But we do have an equation. That is how we defined epsilon, right? We have known that epsilon equals what? Equals delta over L, right? So delta BC can be calculated from epsilon, right? This it equals epsilon BC times LBC, right? But do we know epsilon BC? Right, we don't know. We don't know that yet, right? We don't know epsilon BC. Right, but how can we solve epsilon BC? We don't know the deformation. So based on the equations from chapter 1, we have no way to calculate epsilon BC. But we just learned Hooke's law, right? What is Hooke's law? Hooke's law told us that the stress equals E times strain, right? So the epsilon BC can be calculated from the stress in BC over E, right? But here, do we know delta BC? Do we know sigma BC, the stress? No, we don't know yet, right? We don't know yet, but we can calculate it from the force and cross-sectional area, right? So sigma BC equals FBC over A, right? So here we just need to determine, at the first step, we have to determine FBC. Right? So we will need 4 steps. Basically, this is the first step to determine FBC, and the second step to calculate delta sigma BC. Then the third step, we will use sigma BC to calculate epsilon BC. Right? Then the final step, we will calculate delta BC. Right? So we have these 4 steps. Right? So first step, second, third, and the final step. Okay, it's clear now. So as the first step, we need to find out the internal force FBC. So how can we do that? How can we find the FBC? Do we need free body diagram? Yeah, we're determining the internal force. Okay, the internal force in BC. So we need free body diagram. Okay. Just let's look at this structure. Here we have point A here, point B here, right? The FBC is here, right? FBC, and let's see, here is point O, and we have a P downward. That's all, right? So we have cut it off and make it free, so we can add the restraints. Okay, at point A, it's a pin support, right? So we can add FAY, FAX, and FAY. Right. So based on this, we can list several equations, equilibrium equations. Right. Sum Fx equals 0. We got Fax equals 0. Right. Sum Fy equals 0. So we have Fay plus Fbc minus P equals 0, right? And we have the third equation, sum M about point A equals 0. Right, we have FBC times LAB plus PA equals 0. Is that a correct equation? Is that plus or minus? Right, they have different directions, right? Minus PA equals 0. Okay, so the FBC equals PA over LAB. Right, that is 12 kips times A, that is 4, over AB, that is 5. Okay, so this is 9.6 kips. Okay, so as we just analyzed in the second step, we will use the definition of stress to calculate the stress. Right, BC will use this definition of normal stress equals internal force over area. So from here we can calculate the normal stress in BC. Right, that is FBC over A. FBC has been calculated. That is 9.6 kips. Right. How about A? Right, so A, it's a rod with a diameter of 1.5 inch. Right, that A is pi over 4 times 1.5 square. It is 1.767 square inch. Right. So here we have 9.6 kips. Well, that is 1,000 pounds. Right, over the area is 1.767 square inch. Right, so we'll get 5433 psi. Okay. So if you are not adding this 1000, the result should be 5.433 ksi. Right? It doesn't matter. You can make your own choice. Then the third step, we will use such an equation to calculate the strain, right? Strain. The strain equals sigma over E, right? This we derived it from the Hooke's law, right? The Hooke's law said sigma equals E times epsilon, right? So we derived it from the Hooke's law. Then from here we can calculate the strain of the rod BC, right? It would be sigma BC over E. Right? Sigma BC is 5433 psi over, it's said here, okay, 29000 ksi psi, right? Equals what? Equals 0.000187 strain, or 187 microstrain, right? Okay, then our final step would be just to solve it, right? To solve the deformation of BC, or displacement of point B, right? The last step, we have delta equals epsilon times L, right? So the delta BC equals epsilon BC times L BC. That is 0.000187 times 3 feet, right, times 3 feet times 12 to turn it into inch, right? So we get 0.00674 inch.